I meant to actually record textbook homework problems, but instead of doing the textbook homework, I went through and did chapter 14 online homework and got that set up. As the semester goes, you might start to notice that the homeworks are all sorts of out of weird order, and that's because the Kinect system, as far as I'm concerned, is awful as far as trying to generate homework assignments. So the first two I tried to set up so that they went in sequence with the textbook, either the textbook or the lecture sequence. Okay? Remember, the lecture is slightly out of sync from the textbook based on the things that I think are more important or easier to discuss. Okay? So the homework problems should kind of flow along with the lecture or the textbook, depending on what I set up. Okay? For chapter 14, I'm positive it's with the lecture. Okay? Like I said, later chapters, they may just be shuffled all over the place, so jump through the homework assignment, picking and choosing problems as you go. Okay? I should have textbook problems by tomorrow. So we looked at some factors that affected rate, and we started to discuss some of them. So far, all we've really addressed is our nature of the reactant. Okay? So what physical state are we looking at? Okay? And for this semester, we pretty much said we're only going to deal with concentration and pressure. So solutions and gas phase systems are the only things we're concerned about. Okay? We then went through and picked an individual experiment. We looked at a table of data and said that table of data is difficult to interpret, okay, because there's too much information there. So we converted all of that data into a figure, and that's where we got the graph. Okay? We could then go through and start to pull information out of it about rates. Okay? So how fast did the reaction go? How fast was one reactant consumed? How fast was one product formed? Okay? So we could evaluate those things. Okay? And what we ended up looking at was our rate of change. So we've got now a formula for this and a new equation. Okay? So if I'm going to look at a rate, we'll look at the change of one species with respect to the change in time. Okay? And if we wanted to, we could go through and compare this across our data set. And that's where we get these large differences. So we pick the beginning and the end of the reaction to look at an individual rate. Okay? And when we go through and do that calculation, we started with our final concentration, our final time, and we subtracted our initial. Why did we do final minus initial and not initial minus final? If it helps, I don't really know the answer to this. I'm curious to see what you say. Any ideas? What's that?
To keep it like in the right negative or positive.
We'll address that in a second, but it doesn't fix that. In fact, it actually propagates that issue. Why do we always do final minus initial?
Someone came up with it, it works.
That's the best answer I've got too. Okay? It's our standard notation. So we're trying to keep things as consistent as possible, and when we look at a change, we look final minus initial. Okay? It could have easily started initial minus final. Our signs would change around, and so ultimately all of our calculations and everything thereafter would have to account for that change in signs. Okay? When we're typically looking at a reaction, we're concerned about where the reaction goes to. So we say our primary importance is our product, okay, or our final position. So we can say final minus initial. Okay? So just kind of remember that when we look at our changes. Okay, so we could relate this back to our individual reactions. And we could look at a rate of change for C. Okay, what is C? Reactant or product? It's a product. What is A? Reactant. So we're using the balanced equation. Well, take my word for it. Okay? We're using an equation, which is in theory balanced, to kind of determine whether things are products or reactants. Okay? And as simple as that observation may be, it makes a huge impact on the signs of our numbers, okay, or the signs of our answers. So if we're going to calculate the rate of change of C, we would go through and do our simple calculation. I don't think I quite give you the next number. Yeah, let's step away from that. Pretend you didn't see that. Our rate of change of C. So C is a product. Okay, what sign would we expect on that number? Okay, why should it be positive?
Combination.
Being made. So if we do our final position minus our initial, initially, how much product is there? Nothing. Finally, there's something greater than 0. So we have a large number minus a small number, we get a positive value. So we would expect a positive value for the rate of change of our products. What happens with our reactant? It decreases, so what should our rate of change be? What should the sign be? Negative. Okay? Again, simple observations, but they make a huge impact in how we calculate things. Okay? How could we see this within the graph? Let's see, did I put it up on the next one? If we take a look at our product, what's the slope of our product? Positive or negative? It's a negative slope. There's our rate of change. What happens with our products? Positive. How do we know positive and negative? If I read right, that is my right, isn't it? Yeah. Right to left, do we say positive and negative? No, our signs would seem to change. So again, we run into a notational thing. When we look at an individual graph, how do we read it? Left to right. So when we look at our left to right positions, we look at our left, and as we translate to the right with our bromine concentration, what happens? It decreases. There's our negative value. Okay? So this information does show up in our graphs. It just becomes a little bit more hidden. Okay? Kind of makes sense so far? Okay. Yeah, I didn't want that quite yet. What happens if we go through and run an experiment, and let's say instead of starting with just reactants and no products, we start with a mixture of reactants and products in the same container? Because when we're looking at an actual reaction, okay, particularly in the real world environment, we're probably going to see a mixture of reactants and products. Okay? And if we're going to decide to monitor that reaction, okay, as we look at these, what does it mean if we see C, our rate of change for C, having a negative value? Is that possible? Yeah, it is absolutely possible, but it's supposed to be positive. So what does it mean if it's negative? It's the one reacting. So instead of this being a unidirectional reaction, we have to start to understand that that reaction arrow ultimately can go backwards as well. Okay? Again, kind of a relatively simple observation, but it has huge implications with our overall calculations. Okay? And again, it introduces this new kind of concept of what is our frame of reference. When we look at an individual reaction, when you look at that reaction up there, what's your reactant? Which side is it on, left or right? It's always on the left. What side is your product on? Always on the right. Okay? So our frame of reference is to always maintain that. When we run through an individual experiment, we may notice that our initial assumption that our reactants were on the left and our products were on the right was wrong. Okay? But that ultimately doesn't matter. What we're trying to do is come up with our best guess as to what happens. We let the experiment decide which way that arrow is dominant. Okay? And we're going to spend a lot of time looking at what implications fall out of those double-headed, or those two arrows, when we move into chapter 14, 15, and 16. Okay? At this point, we're going to be primarily concerned with the unidirectional reaction. I bring it up now because this brings up this negative and positive issue. Okay? Well, let's go back to that. So we've already addressed if we have a negative value for our C value, or our product rates, what we're saying is our reaction is running in the reverse. Okay? So it's a frame of reference. We're always coming back to this frame of reference. So the example that I like to come up with is, as I'm pacing back and forth, I want to know my speed in that direction. It's positive or negative? Positive. I'm moving in that exact direction. What's my speed in this direction now? Negative. It's all the frame of reference. I have to decide where my axis is. Okay? As soon as I've defined where the axis is, I can now start to imply that positive and negative. Okay? So you have to make sure you're aware of what you're looking at and use that very, very carefully. Okay? And that's where these signs come from, our positives and negatives. Okay? The rate of change ultimately has no real positive and negative beyond our standard axis, x and y. Okay? So when we move in one direction, we're assuming we're moving left to right. Okay? Reactants to products. What happens if we decide to get English involved with this? Okay? Someone's going to come along and say, ultimately, it was probably a chemist because we're pretty awful at mathematics. I don't like negative signs. Okay? Those negative symbols are just ridiculously difficult for me to interpret. They mess with all my mathematics, so I want to get rid of them. When we look at the rate of disappearance, we now have this magic negative symbol show up in our calculation. Okay? So we may have kind of fixed our issue, but really we still have that negative. What is that going to do to my value, for my answer, for the rate of disappearance? Should my rate of disappearance of A be positive or negative now? Should be positive. The rate of change, our rate of change was in here, was the, come on now, there we go, was this guy. That value was negative. If I want a number that's positive, how can I change a negative value to a positive? Multiply by a negative. Okay? So you have to now watch out. Are we looking at a rate of disappearance? Are we looking at a rate of change? Are we looking at a rate of appearance? Okay? What these two words do, appearance and disappearance, is change our frame of reference. Okay? So in the example I looked at before, I only looked in this direction, which is left to right, isn't it? Yeah, good. 50-50, I got it right. When we walk this direction, it's a positive value. When we walk this direction, it's a negative value. Okay? So as our reaction progresses forwards, we get a positive value for our products. Okay? There's our rate of appearance for our products. Now when I switch to rate of disappearance, I no longer say I'm looking in this direction, I'm looking this direction. That doesn't work. Let's try that. Okay? So now when I walk backwards, what's the sign? It's positive, even though I'm walking backwards. Okay? So that negative sign affects how we run our calculations. It affects what number shows up. So you need to make sure that you know what you're looking at and when to include the negative and when not to include the negative. Okay? It seems like a simple thing. Oh, that's not going to be that difficult. I'll never make that mistake. Okay? You'll never make that mistake until you get a multiple choice question where you have two answers. One's positive and one's negative with the exact same number. Okay? That will show up, guaranteed. Okay? So you need to make sure that you know what those signs mean, when to use them, when to remove them from your answers. Okay? Questions about that? Okay. Your rate of appearance will always be positive. Okay? Assuming that your reaction is progressing reactant to product. Exactly right. Left to right. Your rate of disappearance will also be positive, because we've included the negative sign in our calculation. Okay? So again, it's changing our frame of reference. Along the lines of exams, I don't know if you guys have noticed, I did post all the old exams. I believe all of them from 2 years ago and last year. So you've got access to those. You can take a look at what types of questions I ask. So you can get a feel for what kind of things to see as well. Okay? Okay, so now what we're going to do is start to incorporate stoichiometry into this. Okay? If our reaction goes to completion, if I start with 1 mole of A, how many moles of C are produced? 1. How do you know it's 1? Okay? The mole-mole ratio that we find in our balanced equation. Okay? What happens if I start with 1 mole of A and I make D moles? Or sorry, how many moles of D are produced? Okay, 3. Again, from our stoichiometric equation. Okay? When we calculated a rate okay, for these individual reactions, we took the change in concentration of A versus the change in concentration, or sorry, the change in time. Okay? If I want to convert this into D, we could then incorporate some units here. I get moles of A. Whoops, that's seconds, not moles. Let's try that again. If I want to now convert that into D, okay, instead of that being an A there, I want to convert it to D. What conversion factor do I need to incorporate into this? What's the relationship between the moles of A and the moles of D? Whoops, I did that backwards, didn't I? Okay. And now when I go through and look at my result, I now have ultimately the rate of change for D. Okay? Close. When we swap across, we're also incorporating a minus sign that we'd have to watch out for here. The rate of A is related to the rate of D, but if we just look at our changes here, concentration of A, our first value here, let's use colors, so if you read it later. If we look at this first value, what sign is that? Positive or negative? It's negative. Okay, we're looking at purely the rate of change. If you go back to that previous slide, remember I boxed in just this conversion, okay, or just that relationship. That is a negative sign. We're looking at our reactant disappearing, okay, or turning into product. So its concentration goes down. We get a negative sign. If we incorporate our conversion factor here, 3 to 1, great. We've now converted the units across. What sign do I get at the end? Positive or negative? Follow the mathematics first. Negative. What was D? D is our product. It's actually forming. So our mathematics is missing something. We can't relate the rates of change. What do we have to relate? The rates of appearance and the rates of disappearance. Okay? So how do I relate the rate of disappearance to D? What do I need to add to this to account for the rate of disappearance? Because right now, this is just the rate of change. I put the negative sign out front. Okay? So when we're doing our conversions between individual reagents, we're converting or forming a relationship between appearance and disappearance. It's no longer a rate of change. Anybody getting confused by that minus sign yet? Okay? That negative sign allows us to say we're looking at a disappearance, which then ultimately washes out our negative and allows us to get to our concentration of D, or our rate of change for D. Okay? I think this next slide. Okay, so now what we're looking at is that our concentrations, which we already established, are all proportional to each other through the balanced coefficient equations. So if we want to propagate this out further, okay, we could, and we just established this, that our rate of appearance and disappearance are related to each other across the balanced equation. Okay, so we can propagate all the way out, and instead of looking now at a proportional, we know exactly that constant that allows them to be proportional to each other. That constant comes from your balanced equation. Okay? And we end up with an equation, or technically a sequence of equation, that relates any element or any product reactant to any product. Okay? Using our coefficients from our balanced equation. Okay? Remember, these must be appearances and disappearances. We're not looking at changes. So when we look at the rate of disappearance of A, what values? So if I want to circle the numerical aspect of the disappearance of A, what pieces of this structure do I need to circle? Should I circle anything over here? No, why not? Even easier than that. This one's not appearing. What did I ask for? A. Do you see A in B, C, or D? No. Okay. So what we need to circle is some aspect over here. What part of that should I circle? First off, it needs to be a rate. So which part of that first element gives you a rate? That gives us a rate. If I asked for the rate of disappearance, what part of that formula or that section gives me the disappearance? The negative. What's the 1 over A? That allows me to convert the rate of disappearance of A to one of the other species. Okay, so it's ultimately our conversion factor. Okay, this is again where our English shows up. Disappearance implies the negative. Okay, as a quick test. What would the sign be? So positive or negative, so that's nice, 50-50, right? For the rate of disappearance of C. Okay, we'll assume a left to right reaction. What should the sign be? Okay. What's the rate of change for C? Positive. What's the rate of disappearance of C? Now you have to add that negative value in there, and what do we get? Negative. Okay? Does it make sense for it to be negative? If our reaction is progressing towards C, and I ask for that direction, which way am I moving? Positive or negative? Moving in the negative direction. Okay? Does that make sense? Kind of, sort of? A kind of, sort of works too. A half shake? Nothing? Okay, we're getting some. Okay, so work with that a little bit. I do recommend that you take a look at some of the problems from the practice exam, or sorry, the old exams, because I definitely asked that very particular question. Okay, so you've got questions there that you can evaluate and look at with real numbers. Okay? So, we can now look at an individual rate. Shoot, do I have a graph on this? I don't have a graph on this. I gotta go all the way back. Okay. When we look at our individual rates, what we talked about was looking at an average rate. So we took 2 points on our graph, and we did a difference between those and calculated something out. Okay. Well, that rate changed depending on what time we were looking at, what time difference we're looking at. Okay. So if we're going to try and interpret this a little bit further, we want to pick a consistent time frame to look at. Okay? And we only want to look at that particular time frame. So what's the most consistent time frame that we could get? How about from time 0 to 100? Okay, we could pick that consistent time frame for every single experiment. What happens if our experiment goes faster than 100 seconds? We'd have to change the time frame. Okay, what if it takes a ridiculously long time, more than 100 seconds? Okay, when we look at that small little time frame, we wouldn't expect to see much of a change. Okay, so what we want to do is pick a single point to get our rate of change. Okay, so what we're looking at is an instantaneous rate, no longer a bulk change. Okay, so what time frame or what time point do I want for my instantaneous rate of change, or rate of appearance, or disappearance? Whatever you're looking for, not a bad idea, except that's really inconsistent. Maybe one person looks at it at, say, time 100 seconds, another person looks at it at time 1,000. Those rates are going to be drastically different from each other. It becomes very difficult to then compare. What's the easiest point? Every single experiment will have this point. 0. So when we go through to evaluate rates of reactions beyond just these graphs and individual rates of change, we're going to pick an instantaneous rate that's going to be time 0. Okay? How do I calculate an instantaneous rate, though? Everything we've seen so far has been changes in concentrations and changes in time. If I don't have a change in time and I don't have a change in concentration, how can I calculate a rate? What's that? What we'll do is move to calculus and take a derivative, okay? Which is ultimately what we were doing in all those other cases. If we look at our start to end and we calculated the rate, here I go with straight lines again. Oh, geez, I aimed for 300. Okay, if we looked at that one, okay, versus this one, versus this one, those look pretty awful, okay? Ultimately, what we're doing is trying to measure that line. If we don't have a change, what we're looking at is where our line only hits the graph at an instant, at one point. Okay, what we're trying to do is measure, oh man, I can't draw with crap. Okay? So to do that instantaneous measurement, instead of looking at now large changes, we're looking at infinitesimally small changes, and we're looking at calculus. What are we measuring? A derivative of the line, ultimately the tangent line. How do we figure that out? Okay. In the old days, they went through and tried to draw a tangent line that just hit at time 0. Okay. In our current time frame, we've got calculus and mathematics to go through and help do that for us, and we can solve for the slope of that line at that instant point, and we can get a rate value. Okay. So when we report our rates, we can now use that instantaneous rate, and we can now come up with a table of rates, okay, for this individual reaction. Okay, great. We now have more data to look at and analyze and decide if that's actually good or not. Okay? So what did we decide about tables to begin with? Not particularly easy to work with, so what do? We graph it. Okay? What we're going to be concerned about now is what this rate term does. So one of our axes should be the rate. Okay? This rate is dependent on either the concentration and the time. Because it's our dependent variable, it goes on the y-axis. So now the question becomes, is what do we put on the x-axis? In the day and age where we've got computers, what do? Plot them both and see if we see anything cool. Okay? What would be cool? I know it's kind of boring, but what's something cool that we could see on our plot? A straight line. Why is a straight line interesting? A curved line is also a relationship. Getting towards it. Straight lines are easy to interpret. Okay? We now have computers that can propagate and fit curved lines. But remember, go back to the olden days where we don't have a calculator, or we don't have a computer to go through and try and fit this data. Okay? Pretty much the only thing we could interpret was how to get from point A to point B. Ultimately, a straight line. So we go through and we plot these, and since I think I only plotted one, let's see what happens. Yep, I only plotted one. Okay? We plot, in this case, our rate on our y-axis versus our concentration. Interestingly enough, what do we find? Perfectly straight line. Okay? We didn't see that in our initial plots. Remember, those had a slight curve to them. Here we now have a complete straight line. We can now prove that there is a direct relationship between the rate and our concentration. Okay? And we could now go through and try and propagate this out and see what that relationship is. Okay? That relationship is ultimately going to be the slope of this line, which is going to be a constant. How do we know it's a constant? It's a straight line. Okay? The slope didn't change. Okay? So what we now have is a relationship between our rate and our concentration that are connected through some standard constant. Okay? So we've got our relationship now, which is nice. We incorporate K as our rate constant. Why did we pick K? Because someone picked it. Okay. Maybe a German, because rate certainly doesn't begin, or rate constant doesn't begin with K. Okay? There was probably a reason behind K, but we don't have that now. So we now have this direct relationship. We could go through and propagate to different experiments and try and see what happens to this rate constant. We could also evaluate and see what happens to our reaction, okay, when we change our concentrations or if we want to change the rates. And we can use that constant to help us predict stuff. Okay, what stuff can we help predict? I guess before we get into it, we want to look at a couple other things first. Okay, this first sentence may seem obvious. It's going to become more important when we move into chapter 14 next week. The rate constant K is lowercase. It's a lowercase k, not a capital one. Okay, what are the units on that K? Okay, so what we can do, because I don't think I just got it neatly written out. No, I don't. What are the units on rate? What's that? It's going to depend on what we're looking at. If we're looking at a reaction, so we can avoid distance. An individual reaction, what two things could we look at? We only looked at one so far. Our concentration. So we could look at a constant, whoops, that was not the button I wanted. We could look at a concentration which has units of capital M for molarity. We could also look at pressure. And we'll evaluate how those two are related at a later date. Okay. What's our other thing involved in our rate? Time, which has units of usually seconds. Chemical reactions typically occur on the second level. Okay. Sometimes we can push faster than that, but our standard will be seconds. So if we're going to look at a rate, what are the units of our rate? Molarity or pressure per second. Okay, we'll include K here just for the moment because we don't know what's going on with that. What are our units on concentration? Molarity. This equation must work. Those units must somehow match each other up. Okay, that's what we learned in 151. Units always must cancel and work out. We'll do an exception, chapter 14. Okay, so what do the units on K have to be? Okay, we could go through and pull algebra out of this, so I didn't really give myself a lot of space. It'd be interesting. We could solve for K. K equals molarity per second times 1 over molar. So we divide both sides by our molarity. We get K left by itself. What do we get for the units on K? 1 over seconds. So for this individual rate expression, the units on K are 1 over seconds. Okay? So it's interesting because it's not unitless. It actually carries some units with it. Why do we need those units? To make sure our equation works. If our units don't cancel out and match up, our equation becomes invalid. So that rate constant must carry some unit value with it. Okay? This happened to be the rate expression for this reaction. Are all reactions the same? No. Which means we could end up changing our rate constant. So let's say we take a look at another reaction. Okay? In this case, the rate is equal to our rate constant times the concentration of, let's go through and say it's, wow, stop that. Reactant A times reactant A. What do the units on K become in this case? What was that? Rate was molar per second. K. What are the units on reactant concentration A? Molar. What are the units on reactant concentration A? Solve for K. What happens? K K equals 1 over molarity times seconds. Uh-oh, rate constant K changes. That's a lowercase k, by the way. That's why I said that. Okay. How else could we write that? We've got it in the numerator. Nobody likes the numerator. That's denominator. Nobody likes the denominator. Okay. So we can flip them up into the numerator by putting in that negative symbol. Okay? So when we change our rate expression, the units on K will also change necessarily to allow for the equations to still work. Okay? So be aware of that when you go through and run your reaction, or when you run your calculations. Okay? Other interesting thing. The only thing I've plotted so far was bromine concentration, okay, or our reactant. We also looked at the changes in concentration, and we could look at the changes in rates for our products. And we might want to take a look at those and see, hey, do those have an effect on our reaction? Okay, and when we plot those out, what's special about those lines? They're not straight. So what does that mean? We don't have an easy direct relationship. We would either have to change our experiment conditions in the hopes of trying to build a relationship on them, or we could try and think a little bit more carefully about our reaction rate. Okay? And when we look at our reaction rate, we know our rate is dependent on the concentration of our bromine. And if we start our reaction off, what's the concentration of our products? 0. Okay? So when we start off at 0, what's going to happen with our rate? We're going to see a drastic change in our rate almost right away. Okay? So is the rate dependent on the concentration of products if there is no products? Does the reaction still progress if we have no products? Yeah. So when we look at an overall rate expression, what we're going to put into it are the concentrations of our reactants, and the reactants alone. Those are the only ones that would ever show up in our rate expression. Okay? So what's the next potentially obvious question? Did all reactants show up in it? No, not necessarily. How do we determine if the reactant is supposed to be part of our rate expression? You plot it. You have to go through all the sequence of calculations and determine, is it relevant? Do we see a relationship between our rate and our concentration? Okay, so we'd have to go through and plot each of these individually to determine how that affects our overall reaction. Okay? Lots and lots of plotting. That's what you get to do in lab. You get to do in lab. I just get to watch and laugh. That was kind of a joke. Okay, maybe I will laugh then. Deal with it. So our product concentrations don't end up showing up in our reaction. There is a pseudo exception to that. When could they show up in our rate expression? Biochemistry majors. When we look at more complex reactions, we're looking at something in cellular levels, sometimes products can feed back and turn off reactions. Okay, so you can get feedback loops. What that ultimately means is that product becomes a reactant in the course of your overall reaction. Okay? If that happens, then it is a reactant. It can now be included in your overall rate expression. Okay? But given an individual reaction, if you don't know anything about your product concentrations, you can assume the product concentrations do not appear in your rate expression. Okay? Okay, so the next fun part. We went through and described all of this so that you get an idea of where all this stuff is coming from. Okay, can we do it all without the graphs? No. Okay, if we're doing this in an actual experimental setup, we cannot do it without the graphs. We have to go through and plot everything. Okay? The reason being is that experiments don't always go true to form. We'll see slight fluctuations. We can't do direct comparisons, and things just kind of, in general, fall out of whack. Okay? So you have to go through and plot things. In the lecture, okay, particularly from my perspective, where plotting is a pain, particularly if you don't have graph paper, okay, yes, we are going to come up with a way that we can evaluate these things without having to go through the trouble of plotting everything. Okay? So what we'll do is when we come up with problems, so I'm saying design experiments, we'll design problems that give easy approximation and comparisons so that you can directly see relationships without having to go through and do these massive amounts of plotting. Okay? And we can kind of do that in the lab. We can design our experiments to give us as close as possible to these easier approximations. So now let's go through and see what we can do with this. Okay? So these are the experimental rates for this particular reaction. Okay? And we want to figure out our rate expression. Okay? So what is the beginnings of our rate expression? First off, we're looking at, oh, stupid buttons. Come back here, buttons. We're comparing rate to what? Concentration. It's a good thing to include. Concentration of what? The reactant. What's our reactant? N2. Oh, was it really that complex? Yeah, it was. N2O5. What else needs to show up in our rate expression? Okay, our rate constant. Okay. According to this, there is a direct relationship now between these two. Do we know necessarily that there's a direct relationship? We done any plots to see that direct relationship? No. So we don't have that data yet, which means ultimately we don't know what this superscript is. This could be times the concentration of N2O5, because it's another reactant. Since I don't know what that is yet, what we can do is put a variable there. We can put in X. That's an X. Okay? So what is the relationship between our rate and our concentration? So what we're now going to do is go to our experiment and try and compare those. If we look at our initial concentration of N2O5, what happens is I go from experiment 1 to experiment 2. I double the concentration. What happens when I look at my rate? Doubles. What does that mean? There's a 1-for-1 direct relationship between those two, which means when I go back to my rate expression, what is X? It needs to be 1. If it was a 2, we'll see a different relationship. We'll see that with a different problem. So X ends up equaling 1. So what you did was just compare these things as quickly as you could and try and come up with that relationship without doing any algebra or mathematics. Okay? And the, shoot, set up the order wrong on this. Okay? One of the things that's interesting about this, which is what that next slide or next piece shows, is that our rate expression does not necessarily fall directly from our reaction equation. Our overall rate ended up being, in this case, come on now, rate equals K to the first power. But if we look at our expression or our rate, it's not a rate, our reaction, we see a coefficient of 2. So those coefficients do not necessarily translate to our rate expression. We must solve the rate expression from the experiment. That requires doing some comparisons to some data. Okay? So let's look at a slightly more complex reaction. What's an acceptable rate law expression for this? What was that?
Would be just K equals bracket.
Close.
And then another one.
Rate equals K, concentration of NH4 plus. Do we know what the relationship is? No, so we can include an X up top. Is there another reactant? NO2 minus, and we again don't know what that relationship is. Okay? So we've got a generic rate expression for our reaction. How would we figure out what this x and y are? We would have to go to an experimental situation where we either plot stuff or we hope that your instructor was nice enough to give you some easy relationships. Okay? So what we want to do is now find some easy changes or experimental conditions that allow us to see simple comparisons. The easiest one to see is when we double the concentration. Okay? But we could triple, we could quadruple, we could do 1.5 times the amount. Okay? Fractions and decimals are difficult, so we almost always pick a doubling of concentration. Okay? So we can go through and now look at a series of experiments. This time your instructor was kind of mean. I stole it from a textbook, so his textbook was kind of mean. I'm just copying. Instead of giving you just 2 experiments to choose from, I'm now giving you a ton of experiments to choose from. Okay? So we would now have to pick our experiments very, very carefully. We said our overall rate expression was potentially dependent on both the concentration of ammonia and nitrite, to our NH4 plus and our NO2 minus. Okay? So what experiments should we pick? Remember, I want to look for 2 experiments for each of these. Okay? I want to pick an experiment or 2 experiments where only one concentration changes. If they both change, they're both going to affect the rate potentially. It's going to be very difficult for me to interpret what the overall result is. Okay? So what experiments could we pick? Hopefully you picked 1 and 2. So we could look at 1 and 2. You notice that our nitrite concentration does not change, while our ammonia concentration doubles. There are other ones, I think there are other ones that we could have picked, but we went for the easiest one to interpret because it's only a doubling. When we go through and now compare our rates, what's the relationship between our rates? Also doubles. What does that mean? Our rate is directly dependent, a 1-for-1 relationship, dependent on the concentration of ammonia. Okay? So now that's one piece of the puzzle. We know what I said x was. I say it was x? Okay, that's now 1. We now need to figure out what y is. What's the relationship of our rate to the nitrite concentration? So now what we need to do is pick another experiment where our NO2 concentration doubles. Well, we don't get a nice doubling there. We do see one here. Do we get our ammonia concentration staying constant? Yes. So what we'll do is now compare those 2 experiments. Whoops. And we see the rate double as well. So what does that mean? Let's see, did I actually write it out? Nope, I didn't. Oh, yeah, I did. We now get a rate expression where our rate constant, or our rate is dependent on the concentration of ammonia and nitrite. Okay, 1-for-1 relationship. We see a direct comparison. Oh, you don't necessarily know that. Let me work with you on that. So if we get our rate, we're saying is proportional to the concentration of NH4 plus, and it's proportional to the concentration of NO2 minus. So what we need to do is somehow combine those 2 pieces of data into one overall rate expression. Okay? If we just said it was rate equals, and put in our k here, our rate constant, that could work for a rate expression, except what happens when I double the NO2? According to this rate expression, what happens? Nothing changes. Did nothing change? No. Which means this expression doesn't work entirely. What we need to do is somehow incorporate the nitrate ion, and that's where we get our overall rate expression, which we put on the other side. We have to add or do a multiplication in there. We can't do an addition because that doesn't give us that direct relationship. Okay? We need to see that straight line coming out of our curve. Okay? Why is this equation now helpful? Okay, what information can we pull from this? Okay, how many variables are there? Okay, we've got 4 different things in there. We've got a rate constant, our ammonia, and our nitrite concentration. Okay, So the fun thing with that equation is if I wanted to solve for one of those variables, what would I need? I need the other three. Okay? So we could go through in individual experiments, solve for our rate constant. Okay? Because if we look at our, come on, there it is. If we look at our experiment, we now have a rate expression, but we had no way of solving for the rate constant. If we go back to our experiment, what did our experiment give us? Concentration of ammonia, concentration of nitrite, and the rate for multiple experiments. Okay? So we could pick an experiment and solve for the rate constant. Okay? Which experiment do we pick? Got to make sure you pick the right one. You pick the wrong one, you can get the wrong answer, right? What did K stand for? Rate constant. So for an individual experiment where we don't change anything except for our concentrations, what should the rate constant be? The same or constant. Okay? So each one of these experiments will generate the exact same value within error. Okay? So we can pick any one of those to generate and figure out what our rate constant is. Okay? That can now be even more helpful. Not quite yet, I guess. Okay? So once we've got that rate constant, we now have an overall expression that we can go through and try and solve for. Okay? So what we're going to go through and do now is end on just trying to go through and solve a beginning to end here. Okay? And I'm pretty sure I set this up so I have to draw it. And okay. So we want to figure out the rate when our concentrations are provided there. So what's the first thing that we could do? The first thing that I would try and do, look for the concentration of ClO2 equal to 0.1. Crap. Okay? Because if I had those concentrations here, why bother to do the calculation? I can tell you what the rate is right off the bat. Okay? So I didn't give you the answer right away. So to figure that out, I now need to know how those concentrations affect the rate. So what I need is a rate law expression for that reaction. So what I've got to go through and do is start it off and see what I can get. So we would get rate equals to our rate constant times concentration of our reactant. How many times do we do that? Careful. Do you know necessarily? No. So that's still an X. Times the concentration of OH minus. Remember how I said products could possibly feed back into the reaction? Okay. How do you know products aren't feeding back into the reaction? So I'm not telling you they are. It's the only time you'll see the products feed back in, okay, where you need to account for them in your overall expression. Okay? So we now have a rate expression. And we've got those variables, and we can now try and plug in the concentration of ClO2 and hydroxide. Great, we can plug those in. What would we then solve for? We could even plug in a rate. No, we can't plug in a rate because we don't know what the rate is at those concentrations. So we don't know the rate, we don't know K, we don't know X, we don't know Y. That's a lot we don't know. Okay, so we're going to have to come up with some way to determine what's happening here. Okay? For each of these individual experiments, what's the rate constant? So what we're going to do is now mathematically solve this as opposed to just looking at data. It's a constant. It's the exact same value. So I'm going to go through and solve for the rate constant for experiment 1. Rate constant for experiment 1 should equal what? The rate for which experiment? Experiment 1. Divided by concentration of ClO2 to some x power of experiment 1 times the concentration of OH minus to the y power of experiment 1. Okay? I know that K1, make sure I pick a good one. Yeah, I know the rate constant for experiment 1 is the same as the rate constant for experiment 2. So let's go ahead and propagate that out. K2. What does K2 equal? The rate for experiment 2 divided by concentration of ClO2 to some x power for experiment 2, OH minus y power for experiment 2. Okay, see how the mathematics gets a little bit more convoluted? We've got lots of letters and symbols now meaning all sorts of different things. Okay? Most of this is just notational stuff. Okay? We're putting in those 1s and 2s so that we know what they mean. That's about it. Okay? And what we said before is we wanted to pick 2 experiments, okay, where our concentration doubles. Think if I did this right, what 2 experiments do our concentrations double? That should be a harder question, I guess. Do any experiments have the concentration double? No. Okay? So we don't, I intentionally removed that easier approximation, looking at the doubling. Okay? So in this case, I picked experiment 1 and 2. Okay? What's the concentration of hydroxide in those 2 experiments? The exact same. So if I wanted to, I could now plug in all of those numbers for each of these. Oof, which I think I'm going to do and probably regret. 0.0248. What are we? 0.06. I can drop the 1s now, the 1s and the 2s, because that's necessarily coming from our expression. Okay? So I can try and simplify it. What's the concentration of hydroxide at that point? 0.3. What does this equal? Our rate for experiment 2. 0.00276 over 2. Yes? Looks like a big mess of numbers. Okay? Which is true, it's going to come out that way. Is there anything that we could do to this to hopefully simplify it? What can we do to simplify? I see the head nod. What do you want to do? So you're saying multiply both sides by 0.03 to the y? So you want to just condense everything to one side?
No, leave them how they are, but just flip the top and the bottom so that you have 0.02x, 0.03y on the top.
Can't just flip it on one side. You'd have to do it to both. So you can do it to both. That's not a problem. But you have to make sure you do it on both sides. Okay? So we could go through and do that in both cases. So really, I think what you're trying to say is we want to get the x and the y variables on the same side of the equation, and our constant value, which has no dependence, with our other constant value. Okay? I quickly ran out of room on this. Okay, so what we end up with, we get 0.02 to the x over 0.06 to the x times 0.03 to the y over 0.03 to the y 0.00276 0.248. Okay. Is that what you were asking to do? Roughly, at least? Okay. Just slightly different than how I would approach it, but it works. What's special about this relationship now? I can now cancel that whole y term. Y is the same in both those cases, so that term drops out. And now I've got one equation and one variable, which means I can go through and solve for x. Okay? So what we should end up seeing when we do this math, if I did this right, we get 1 over 3 to the x equals 1 over, I don't remember the number. Doesn't look like 3, it looks like 9. Okay. How do we solve for x? What's that? Square root won't work because that assumes x is 2. So I see the comparison that you may have seen here. What's the relation? What does x have to be? Can you solve this one just by looking at it? X is 2. What is 1/3 times 1/3? 1 over 9. So what you ended up solving for is after all of that math, you found that x was equal to 2. Okay? You can also go through and use, I think it's 10 to the power of. Okay? So you can raise all of that to a power of 10. The x translates out, and you can end up solving for x in that respect. Okay? So that's a lot more mathematics. What I'll end up doing is setting you up with a system where you can see those relationships a little bit easier. Okay? So I won't make you go through and do the powers. Yes? So we needed k, but to solve for k, what did we need? We needed x and y. Okay? So we did all of this trouble to find x. Great. X is now solved. Can we solve for k yet? No, what do we have to do? Solve for y. Oh, man. So now we go through and do all of this experiment again, except now when we go through and do our comparisons, we want to make sure that the x term hopefully drops out, and we only have to deal with the y term. Okay? I'll pick up with that, solving the rest of that tomorrow, so that you can see the rest of that solved. I would recommend that you do it at home. Once you've got y solved for, then what can you actually do? Solve for k. Then once you've solved for k, what can you do? Actually answer the question, which was solve for the rate. On a multiple choice exam, what answers do you think will show up? Just to throw this out here. The value for x will show up. What else will show up? Value for y. What else will show up? Value for k. What else will show up? The value for rate. And probably something else just to mess with your heads. Okay? Why? Almost all of those answers are correct. They did not answer the question, which technically makes them wrong. Okay? You can still walk out of that. That was fine. Okay?